Welcome everyone. I'd like to share some of my experiences of a project we executed at Sioux where we applied a model-driven development approach. It was for one of our customers who develops electron microscopes. Of course, I will focus on the testing discipline. After a short intro, I will tell you about ASD, which stands for Analytical Software Design. It is the tool and the methodology we used at Sioux to execute this project. After that, I will talk about a bit MDD, model-driven development, and its impact on the testing process. And I will tell you something about specific experiences in this project. I myself am a test engineer. For a bit more than 10 years, I've been in the field. Before that, I've worked as a software engineer for several years. All of my customers are in the high-tech domain, like medical systems, professional security systems, or, as now, electronic microscopy. At Sioux, we have about 300 employees working as software developers, but also as software testers, and we also have electronic engineers and mathematicians. We all work for our customers, and our customers are the R&D departments of several high-tech companies situated in Europe, which you can see on this slide. We have 3 offices in the Netherlands, we have 1 office in Belgium, and we have 1 office in Russia. In Moscow, of course, it is not situated at the place you see in this map because otherwise it doesn't fit on the sheet, but it's the Moscow in Russia. The customer I am talking about is called FEI. It is FEI company, and this company is the world leader in the development of electron microscopes. We all are probably familiar with light microscopes, the traditional microscopes. With them you can magnify the thing you want to see, the object, to about 1,000 times. Which results in a resolution of about 200 nanometers. This is simply limited by the wavelengths of light. You cannot magnify any further with simple light. It's just not possible. With electron microscopes, on the other hand, you can go up to 1 million magnification times. In practice right now of up to 4 million times, resulting in a resolution of 0.05 nanometers. On the right-hand side of this slide, you see a schematic of an electron microscope. In the top, we see the electron source. That's where the electrons come from. The electrons will travel downwards through several accelerometers, and they will travel through a vacuum. Otherwise, they will not get down, of course. In this vacuum, they will hit the specimen. That is the object you are interested in and that you want to magnify. A lot of electrons will travel through the specimen, but several will also bounce back, hitting other material. The electrons traveling through the specimen will hit a so-called fluorescent screen, where the image is in fact being magnified because we have several different electromagnetic lenses in the system. This fluorescent screen can in practice also be a CCD camera, and with a CCD camera you can get the images on a computer screen. In this way we can get magnifications of millions of times. The project we are currently talking about is about the vacuum system. These electrons all travel through different vacuum chambers of different quality of vacuum. And the software of this vacuum system was enhanced and redesigned in this project. And there is where we applied the model-driven development techniques. Let's show you some examples of images being produced with this microscope. Here we see a cancer cell with a magnification of about 5,000 times. In the next picture we see Salmonella bacteria, and here the magnification is already 80,000 times. And when we go even further, we can even see atomic structures, in this example of germanium, where you see the distance between the atoms is about 0.5 nanometers. In fact, this magnification is about 2 million times. Last year, the Nobel Prize in Chemistry was won by Professor Daniel Shechtman, and he has done it with one of our systems you can see in the back of the picture, the so-called Titan. As I already mentioned, we redesigned and enhanced the existing vacuum system, the software of it, and for that we were using a model-driven development approach, and for that we used ASD. That's a tool and a kind of methodology provided by Verum. It is useful in an architecture that is component-based, so your complete system, your software system, is decomposed in several components. And this way you can get existing components out and redesign them, for instance, with ASD, or you can design new components with ASD without changing the complete system, only part of it. The models are being defined by the software engineers in this ASD tool, and they are automatically verified on a mathematical basis at design time, so not at runtime at late phases of the project like in the system test, but at design time. No code has been written, but the models can already be verified in a mathematical way. This is done with a model checker. It's quite extensive and it checks for all kinds of things. The most interesting here are, for instance, deadlocks and live logs, starvations, and race conditions. All problems well known to developers, and these problems, when they occur, are very hard to analyze and very hard to solve, and even harder to retest that they indeed have been fixed. So this is really interesting. How these models are defined in ASD can be seen here. The developer defines the model, and the model needs to be precise, complete, and correct. This is just a requirement. This must be done, otherwise you cannot get the code out of the model. You cannot generate the code. Of course, the developer will make mistakes, and the model he is defining in diagrams and charts and sheets and things like that in the first time won't be complete or correct, so there will be errors in it. So therefore we have the model checker. ASD, the tool, will generate from the model of the developer a formal model, and the model checker will perform all kinds of verifications on this formal model, all kinds of mathematical verifications. All things the model checker sees and finds are reported back to the developer, and the developer should fix these design errors, because that's what they are. They are design errors, no programming errors, because nothing has been programmed yet, and he can fix them. When the model the developer has provided is indeed precise, complete, and correct, we can get the code out of it. We can generate the code in several different languages: Java, C, C++, and C# at this moment. It was the model checker that checked the formal model, but source code is generated out of the ASD model, which was provided by the developer. But the company behind ASD guarantees that the code is equivalent with the formal mathematical model, and the consequence of that is that this code that has been generated is free of things like deadlock, live log, starvations, and race conditions, and those kinds of things. Several different things are modeled. To begin with, the interface of the component or of the different components that are being modeled is inside the model. It is different, defining what the set of components should do. So the interface is in there. Besides that, also the how is being modeled. That's the design model, of course. That is the implementation of all the interfaces, the internal stuff. So the how and the what of all the model components are inside the model. An extra point of this approach is that also the components that are outside of the modeled components are being part of the model, their interfaces at least. The interfaces of not model components are inside the complete model when they are being called directly from model components, of course. And this is one of the strengths of ASD. So it's just a bit larger, the context, than just the model components. Also, the boundaries are inside the model. That's really a strength. Not everything can be modeled within these tools, in this case ASD. ASD is typically suited for things like state machines, sequence diagrams, and complex algorithms. Not all software consists of these things, of course. But the customers we have with the technical systems, and in this case the electron microscopes, we see that large parts of the designs and consequently also the code is about these kind of things: state machines, complex, large state machines, different state machines communicating with each other, large and complex sequence diagrams, long diagrams, and of course complex algorithms. These kind of things can be modeled ideally in ASD. What kind of functionality is being modeled there? of course, the good weather behavior. The normal functionality is modeled there. That is just the functionality the normal software developer always thinks about. So this is also the part he is going to think about when he's not modeling the thing. But when modeling is being used, he is forced to also think about the bad weather behavior, all the exceptional things that can happen, the things he didn't thought about. And this is where ASD comes in. The model checker will just tell him that he forgot, for instance, certain event state combinations and state machines he didn't thought of, but in fact they can occur. So ASD reports it. And the developer should think about what the correct action should be in these state machines. And also illegal behavior is interesting, because when ASD occurs on illegal behavior, it will report this. This can be in an assert or a crash or whatever, but when ASD itself gets into problems because one of the handwritten code components does something he doesn't expect, ASD will just stop because he cannot guarantee the success of the upcoming functions. Then it's probably more wiser to stop. There are also possibilities to do this in another way, but we chose this way. So we see we can model a lot with ASD, but definitely not everything. In our case, it was about 2/3 of the code of this redesign could indeed be generated with ASD. So that's quite a lot, but not everything. They're still handwritten code. Let's take a look at the V model. Where are these formal methods, this modeling, taken place? It is in the lower parts of the V model, at the design level, or even part of the architecture level. Not up there to the system requirements or even to the user requirements. There we did not use it, and ASD is not really suited for that. ASD's strengths are at the design level. From the design, you can generate your implementation. So the formal methods in this case are applied at design level, or maybe a bit in the architecture phase, but not above that. And as mentioned before, it is only in software. In our systems, we have more disciplines to cope with. With hardware, we have electronics, we have optics. We only model the software part here, and software is only one of the things. And even not all the software, but only part of the software, for instance, the state machines and the sequence diagrams. So it's just a tiny part that has been modeled in the complete system. But for this redesign, we had quite a lot modeled here. When we look at the testing activities at the V model, we see, for instance, that the component test is in fact not needed anymore, because the code will be generated out of the model. And in fact, when you're developing component tests and run those component tests, in fact, you're testing the code generation. That's not the part. That's not the idea, sorry. The component tests, at least the white box part of the component test, is not needed anymore. On the other hand, of course, the model can still be incorrect on a functional way. So probably you will want to review this model or even test it. And we did that in this project. So we spent a lot of time reviewing those models. So what we see that the testing activities of the software engineer will get less. And that's not a bad thing, because most software engineers don't really like implementing component tests. And part of the component tests can now just be skipped because the code is generated. So that's an advantage. The test activities of a test engineer, on the other hand, well, from about the integration test level up, all the test activities of the integration test, the system test, the acceptance test, they're still needed. Because we have the integration with other disciplines. We have the integration with software that is handwritten and still needs to be tested. But we can definitely say that model-driven development has impact on the qualities that are on the quality of the deliverables that need to be tested. So the testing of a test engineer is still needed, but it can change because the quality is different of the deliverables. Probably you can focus on other things. Let's look at some of the experiences we had in this specific project. We indeed saw that we still need to test. We just did our normal testing and it was needed. We did our integration, the integration on software level with other software components that were handwritten or that were legacy components, of course. We redesigned several components, but a lot of components were just unchanged. So the integration of those different components need to be tested, of course. We needed to test the integration with the hardware and with the mechanics. Still need to be tested. We also need to test on system level that all the functions are working correctly. And here we also saw that when the model is incorrect, the code can be 100% correct according to the model, but when the model is incorrect, the code is incorrect, of course, too. It's just a principle of rubbish in, rubbish out. And of course, what you normally see in projects, new insights, you get new ideas, the product managers get new ideas, and so the model needs to change. But that is possible. It is quite easy to change the model with new requirements, with changing requirements, with incorrect requirements, and generate the code out of it immediately. We still verified all kind of functionality, and we still found errors, functional errors. What we didn't find were any programming errors or integration issues in the generated components. We found programming errors in handwritten code, legacy handwritten code, or just other components that were changed without using the MDD approach. We found programming errors there. We found integration errors there. We found also several integration errors on the boundary between generated and handwritten code. And that's quite hard to analyze because the guy who wrote the handwritten code most of the times doesn't understand the models and vice versa. So there we have some communication problems. So it's quite hard to analyze those issues. But we didn't find any programming errors in the generated code themselves. We were free of programming errors. Well, that's a big benefit. What we are doing with our systems a lot at this customer are reliability testing. It is nice that a certain function on the system is working correctly, but we also want to make sure that the most important functions of these systems function all the time. So not once or twice, but 1,000 times after each other. Or the system needs to be up and running 24/7. So we are testing for this, and we're doing duration testing and stress testing. And what we witnessed there is the reliability of this generated code is very high. It's rock solid. In fact, we didn't find a single reliability issue in the generated code, while we found multiple problems in handwritten code in this project. So this is really one big advantage of this approach, is the reliability of those components. It's really high. And what we in fact saw when we were reliability testing this vacuum system, which we redesigned with this tool, with this approach, is that we immediately found hardware failures and hardware wear much earlier than in other projects. That's because we didn't hit on software failures. We found those hardware failures and the hardware wear on certain parts of the mechanics much earlier. What we also witnessed is that during the integration and the system test activities, we didn't find that much reliability issues. We found reliability issues in handwritten code, but not in this vacuum redesign. The result of this was that the integration and the system test were running a lot smoother with less system test cycles. We performed the same system tests, but we needed less cycles because we found less problems and we found less reliability issues. We were used to finding reliability issues late in the project during the system test activities, and when you find them then, it takes a lot of time and a lot of problems to solve those issues. And your project will probably miss some milestones due to that. Let's take a look at the product analysis test metrics. When you're familiar with risk-based testing, then you will know these pictures. On the x-axis, we see the impact. On the y-axis, we see the likelihood. And we see several dots. These are the different components in our system. And what it means is, for instance, when you look at component 1, the likelihood is high. That means the likelihood on defects in this component is rather high. And the impact is also high, which means the impact of possible defects is also very high. So this is a critical component. And we are using the Moscow matrix for this. And we see that quadrant 1 is the must test quadrant. So this is the components in this quadrant are the most important ones. These must be tested very thoroughly. And we're seeing quadrant 2 are the should test components, quadrant 3 are the could test components, and quadrant 4 are the won't test components. Well, maybe you should test them, but very lightly. And in fact, this matrix, this product risk analysis test matrix, you can use this perfectly to define your test approach of your complete test project. Let's look at component 1. Let's assume that this is the component of the vacuum redesign. And we are developing it with ASD, and we generate the code out of the components. What does it change on this component compared to a handwritten component? When this is the place in the matrix when it was handwritten, we can see that the impact will stay the same, whether it's handwritten or generated, because the problem in this component will result in a system crash, will result in an unuseful system, may even result in machine damage. So the impact will not change, whether you are writing this code with your hand or using code generation techniques. The likelihood, on the other hand, that will change. It will decrease dramatically, because you're making less programming errors, you're having less reliability issues. So the likelihood of this component will decrease drastically in this way, so far that it gets into another quadrant. So what we're seeing is that we still need to test these components also when they are generated out of models, but the way we test them, that can be differently. We can use less formal test techniques. We can use less time on these test techniques. So we still need to test them, but the test techniques will change, the test approach will change. Probably we can focus on other components that are still in quadrant 1. So we can choose, or we can use our testing time more efficiently that way. And some conclusions and a summary of the things I've been telling you. We saw that the component tests, at least the white box part of the component tests that are focusing on the internal workings of the component, that probably can be skipped, because the code itself, the internal working, is correct. That is guaranteed. And that is also what we saw in this case study. The internal working of these components is just correct. Maybe a component test is still useful on a black box variant, because the functionality can still be incorrect. So it makes sense to check the functionality on component level. Absolutely. The integration and the system testing will go a lot smoother, at least on the components that are generated, that have generated code. What we saw, much less interface issues and less reliability issues. And the reliability testing we are performing in this project extensively gets into a reliability measurement instead of testing. We are not finding any software defects anymore. We can really measure the reliability of the total system. We can measure the reliability of mechanical parts and things like that without being hampered by software issues. The integration and the system test can be performed much more efficient. In our case, we used the same set of test cases. We didn't test less test cases because we generated some part of the code, but what we saw, we found less issues, and so we have less retests and less cycles in the system test. So the system test itself was shorter. What we saw, on the other hand, is that the architecture and design work of the software engineer takes more effort. That's of course understandable, because the software developer has to think about this bad weather behavior and all the illegal things that can happen. Normally, in other projects, we saw that he still needs to think about them, but that was part of the integration phase. Now, those thinking is part of earlier project tasks, which is better, of course, but we see that the design tasks take more time. But this is an investment, of course. Our experiences with this redesign with ASD, with model-driven development, are so good that we are now looking at other components that can be redesigned with ASD. So we'll use it in more parts of our electron microscope system. In one of in several slides, we saw the V model, and in fact, we're using the agile methodology in our software development way. So we're not looking at the V model that much. What we see is this is MDD techniques fit perfectly in an agile way of working. So this is really nice. So now there's room for some questions for the audience.